You should have found out in your homework last night that two of them ended up saying ASS, 15 and 23. And ASS is not one of the ones that allows us to say they're congruent. So does that mean they're not congruent? Well, this is where we're going to start with our discussion today. Why ASS doesn't work. If I have an angle, and I know this angle, but I don't know this particular side length. I do know this side length, it's fixed. And although I don't know this angle, it's like a hinge, it could be swinging open or closed. I know this side length. Initially, we might think that there's only one place this hinge can swing open to that actually hits where this angle finishes. Therefore, this looks like one triangle. I can visualize a triangle using these three pieces of information, and it seems pretty significantly locked in. But it turns out this side could also swing around over to here. And it would still hit this line, but now it would produce a very different triangle. The most obvious thing is this is an acute triangle. This is an obtuse triangle. They're not congruent, and yet they share the ASS information. This is called the ambiguous case because there's two possible answers. Now, again, it's ambiguous. It's not that it's always wrong because there's a couple possibilities here. If I have that same information, but the third side is long enough where it has to hit out there, and if I tried to swing it around, it would be on the back side here, then there is only one triangle. So there are some situations where ASS does work. The other place where ASS works is when that triangle is a right triangle. Because even though it appears it's ASS, since this is a right triangle, whose theorem do we know works? The Pythagorean theorem, right? And if the Pythagorean theorem works, then we could actually find, oh my, I haven't been sharing the screen with those on Zoom at all. Okay, so this is why ASS doesn't work. Here's the picture, here are the two possibilities. But if it's a right triangle, and I know the hypotenuse, and I know this side would just be a function of those two, wouldn't it? Because a squared plus b squared equals c squared. So if this is a and this is c and we don't know b, b is just going to equal c squared minus a squared, square rooted. In other words, by knowing those two sides, we know this one. So we really do have a side angle side scenario. So you'll remember when we did this on day 51, there was another item down here that we didn't talk about. It says HL. I prefer to call it RHL. It is the scenario of having a right triangle where the right angle is the known angle, this leg is known, and this hypotenuse is known. And that's what we're going to talk about today. So you should have this packet in front of you. What we're talking about is the theorem called RHL. Just like SSS or SAS or any of the others, it requires three facts and evidence to claim that the triangles are congruent. In this case, if we have angle BAC and angle EDF are right angles, that satisfies the R. If we have the hypotenuse, which is the longest, the slanted side, the side opposite 90 degrees, as a congruence pair, that satisfies the H. And then we can have either of these other legs, it doesn't matter. BA is congruent to ED. Then by RHL, we have enough to say that the triangles are congruent. Triangle ABC is congruent to triangle DEF. And that's by RHL. So what does that look like for us? Well, let's go down to number 1 here and we'll do a proof with it. We've got a given. We know that these are right triangles. The designer of this worksheet does a very good job, but I will say that I kind of disagree that they haven't clarified where the right angle is, because that matters. Personally, what I would like to see is another step in between, like 1.5, where you would say MPL and MPN are right angles by the definition of right triangles. But this one's a little truncated. Then I know that ML and MN are congruent. That was given to us. And once it's in my statements here, I get to mark that congruence on my picture. And that gives me 2 pieces of information. But how many do I need to prove triangles are congruent? 3. So what's the third one that's hidden in here? Good. MP has to be congruent to itself. Since it's a congruent statement, it's going to be the reflexive property of congruence. That then gives me my 3 pieces of information necessary. If I had taken these right angles one step further to say, because they're right angles, they're congruent, I would have ASS. It doesn't work for us. But this is that special case of ASS. If it's not any old A, it's a right angle, then you don't take it as far as saying they're congruent. You just leave it at it's a right angle. You have the hypotenuse and the leg. So we can claim that these 2 triangles are congruent by what theorem? RHL. And again, some people call it HL. I like using all 3 because that's consistent with the other theorems where you have to have S, S, and S, and SAS, etc. Any questions on that first theorem, first proof? Okay, please do the same type of thing for number 2 yourselves. Again, she kind of truncates the right angle thing, but you will need the definition of midpoint for that one. Give it a try. Guys need another minute on it?
Yeah.
Okay. Okay, let's take a look. So the first step here, it tells us it's a right triangle. Again, my preference would be a step in between that tells us what the angles are that are right. I think they intend this, which in fact gives us the R we need. Then they give us X as the midpoint of WY. That doesn't allow us to put anything up here. It's not a congruent statement, but it leads directly to one. What's the congruent statement I can build out of the fact that this is a midpoint? WX equals YX, good. Or congruent to YX. And what would be my reasoning for that? Good, we said there's a midpoint and we're using that fact to determine this. So that's the definition of midpoint. Well, WV is different.
Well, I have a question.
Yep.
Can you write down WB is equal versus convert to WV?
I haven't written that down yet. I went first, second, then I'm coming third. You know how when you make a pizza, you can put down the crust first, then the sauce, then the cheese. Then it doesn't matter if you put down the pineapples first or the ham first. It just makes some people gag at the idea of a Hawaiian pizza. But of course, there are some things that do matter, right? You can't put the sauce down before you put down the crust. So in the same way, I can't say that the definition of a midpoint applies until I've already said that there's a midpoint in place. That requires this order. But this little chunk of 2 and 3 could have come first. It could have come third and fourth. That's not as important. So WV now is congruent to YZ. That's given. And that lets us directly translate something up to our picture. And now we ask ourselves, do we have the 3 facts we need to prove these 2 triangles are congruent? In this case, we do, right? We can say triangle WVX is congruent to triangle YZX. The reason is RHL. I got my R here. This looks like my H. This looks like my L. Any questions on writing this proof? What's your confidence? 5, easy peasy. I can do this all day. 3, I missed one little step in there, but I think I could do it right next time. 1, this is hard for me. I don't understand this. Okay, good. All right, please flip to the next page. So we've been working with proving triangles congruent because it creates a grouping of triangles, things that we can say are true about more than one triangle as a set. One of those sets we're going to be working with are triangles that are called isosceles triangles. So first, let's get some terminology, some nomenclature. This is an isosceles triangle. We know that because it's got 2 sides that are congruent. And we're going to call those sides, the congruent ones, the legs of that triangle. The angle where those 2 legs intersect up here at B is called the vertex angle. And the side opposite the vertex angle, in other words, the not leg, is called the base of this triangle. And then these 2 angles, 2 and 3, are angles at the base. They're called base angles. Now, I like to prove any theorem before I give it to you. And what this theorem is asking you to do is recognize what happens every time you've got an isosceles triangle. All the proofs we've been working on have been proving triangles are congruent. So I'm going to use that same knowledge. But what's different about this picture that makes you feel like we can't do what we've been doing? What's different about this picture than what we've been seeing? Colin?
No angle.
No, there's no angle, true. But we've had some pictures where we haven't had angles, haven't we? Some proofs. There's one fundamental issue here. What's going on? True, no numbers. Yeah. Okay, still looking for something else. Yeah, Jack. There's only one triangle. We got to prove 2 triangles are congruent, and we've only got 1 triangle. How can I possibly turn this single triangle into 2 triangles? Put a line right down the middle. That's right. And yet, what does that mean? Does that mean, like, should I draw it like this?
No, like right.
An altitude perpendicular to the base. Is that what you guys like? All right, good. Now, if I make this perpendicular to the base, this pink line I've got is going to be reflexive to itself, is it not? And is this then enough to say these two triangles are congruent? It is, isn't it? By what theorem? RHL, the one we just learned. And so if in fact these two parts are congruent, these two triangles are congruent, then couldn't we say that these two corner angles, the base angles, are also congruent by CP/CTC? Yeah. And that's what we're going to do here as the isosceles triangle theorem. What it says is, in general, if you have an isosceles triangle, and I'm drawing it as an isosceles picture, arrow, then the base angles are congruent. More specifically, in this case, if AB is congruent to CB, then we could say angle 2 is congruent to angle 3. Now, this turns out to be a little bit interesting. We chose to make this an altitude, but we could have split it down the middle, so to speak, different ways. Remember we did this last unit? Couldn't we have made this a median, where it split this side exactly in half, hit the midpoint? Would it still be congruent triangles? This time by side, side, side. Could I have poked out of this original vertex with an angle bisector? Yes. And that still would have worked. I'd have side, angle, side. The triangles would be congruent. And then with CP, CTC, I could say these are congruent. So several ways to come at it. Turns out we could also do it backwards. We can say if I've got a triangle and all I know about it is that these two angles are the same, I can do some proofs. I can drop an altitude again. This is reflexive to itself. These two triangles are then congruent by angle, angle, side, which means if the two triangles are congruent, I can say that corresponding parts are congruent. And so just by knowing that the angles began congruent tells me that it's an isosceles triangle. So this is the converse. If we know that the triangle has two angles that are congruent, base angles, then we know that the legs are also congruent. In other words, if 2 is congruent to 3, then I can say that AB is congruent to CB. Any questions on that? So what does that mean for us here? Please look at number 1. Think about the two theorems we just come up with. What can we conclude? Yeah.
That J is, well, L and J are the same.
Good.
Because JK and LK are
Good. Since we have a pair of sides that are congruent, the base angles must be congruent. So if this is 68, so is this. What about K? Can you?
K is 44, there's a triangle, the angles out to 1.
Good. In other words, the measure of angle K plus 68 plus the other 68 has to add up to 180 because of the triangle angle sum theorem. That means that the measure of angle K plus 136 equals 180. Subtract and you get the measure of angle K is equal to 44 degrees. Any questions on that application of the isosceles triangle theorem? Move down to number 7, please. What do we do here? Fiona? Good. Why? How did you know to do that? Exactly, because the base angles are congruent, the side lengths must be. There we can say, therefore we can say 9x minus 73 equals 3x plus 23. We can subtract 3x. We can add 73. Divide by 6, 136, so 16. Any questions? Yeah, no?
So when it like, oh wait, never mind.
Okay. All right. You'll finish up that page with the isosceles triangles, but this will be the bulk of the homework, and it's not going to be a ton. If you haven't finished up last night's homework, you should have some time today. Let's take a look at number 2. All we're asked to do is write SSS, SAS, ASA, AAS, or let's not use HL, let's use RHL, if it's enough to prove the triangles are congruent. So what about number 2? Is that enough for us? It's only 2 pieces there now, but is there a third piece lurking in the shadows, dying for us to figure it out and unearth it? What is that third piece? Yes, this leg is shared by both of them, so we can call it that it is congruent to itself because it's reflexive. Now we've got enough to claim the triangles are congruent by what theorem? Almost. AAS, good. Okay, what about number 4? 2 pieces of information. Looks like there's not enough. Is there a third piece? Asher?
There's not, it is not good.
Good. You're right. There is enough to have 3 pieces of information. There's only 2 shown. What's the third piece? It's like hiding in here. Vertical angles. But even once you get that, that only gives us angle, angle, angle. And as Asher said, that's not one of our answers. That's not what makes it congruent. Now, I'm going to disagree again with this author on a subtle point here. What the author says is that if it's not congruent, write not congruent. But do we know that it's not congruent? No, all we really know is that we don't yet have enough to say it's congruent. So I'd prefer that we write not enough info. We cannot conclusively say they're not congruent. We can only say we don't yet have enough information to know. Last piece of instruction for today. What about number 6? What do these little symbols mean?
Parallel.
Good. We haven't seen those for a while. They do mean parallel. Well, there's 2 arrows here, and there's a corresponding set of 2 arrows here. So that tells us those 2 are parallel to each other. This has 1 arrow, and this has 1 arrow. So those 2 are parallel to each other. Now, there's no congruence pieces here. We could do reflexive. We know this is congruent to itself, but we need more than that. I'm going to ask that you think about it this way. If you're looking at parallel, I want you to think about if parallel and see what that sparks in your brain. Mary? Or sorry, Kate?
Would the, well, there's 2 like alternate interior angles and stuff.
Excellent. When I'm looking at this pair of parallel lines and I treat this as a transversal, the angle that's formed between the purple and the red and the angle that's formed between this purple and the red are in an alternate interior angle relationship. Therefore, they're congruent. Similarly, if I draw the other side in green, then when I look where the green and the red meet, and the other green and the red, those angles are alternate interior relative to the double arrows. So I've got two sets of angles and the side in between through reflexive. So I can say these triangles are congruent by what? Angle, side, angle, ASA. All right, you're going to finish up with these three on the left. You're going to do the proofs that are listed here. There's 1, 2, 3, 4, 5 of them. Please note, again, there's too few spots to do this proof with the fidelity that I would normally ask of you. For instance, when you're doing vertical angles, you won't have room to say first they are vertical angles by definition and follow it up with if vertical then congruent. So consolidate those and just say these angles are congruent. If they're vertical angles, then they're congruent. Okay, you've got the period. I suggest you work together.